Welcome to Mark's Tech Talk. Today's video will be on electrical safety. We'll consider how you get an electric shock. That occurs when a person has a contact with a voltage, and it's not simply contact, but it's actually contact at two different points at differing voltages. So, for example, you may touch a high voltage with your hand, and your feet may be grounded, and therefore you have two different points of contact at differing voltages, and that's when you have electrical current flowing through your body. And if that's sufficient, that can be quite serious. So we can change that equation a little bit by adding some additional resistance in that pathway between the 2 points of contact. For example, if you wear rubber boots or rubber gloves, that increases the resistance of that pathway and reduces the amount of current that will flow through your body. On the other hand, if you're wearing jewelry or if you're standing on wet ground, that reduces the resistance and increases the amount of current that flows through your body, and obviously that is leading to a more serious shock. So the most common points of contact are your hands and your feet, as we just described, but it might be other things. For example, your head. Maybe you're working on an overhead light fixture and you stand up and your head accidentally touches a bare wire. But it also might be other parts of your body. For example, I'm aware of one situation where a technician was working on a piece of equipment and touched some high voltage, and the second point of contact was actually his belt buckle. He was leaning against the workbench, which was grounded, and he got a ground through his belt buckle. So you should be aware that it's any 2 points on your body, and be aware that it's not just your hands and your feet. So the severity of the electric shock that occurs depends upon the amount of current that flows through your body. It also depends upon the pathway of the current through your body and the duration of that current flow. So as far as the amount of current that flows, you may have seen a chart like this where it gives you different thresholds for different levels of electrical shock. Keep in mind that nobody is going to actually measure this to say, okay, at this point you go into ventricular fibrillation. Obviously that's dangerous, and you wouldn't do that to a person. So a lot of these thresholds are estimated. Even if you have an accident and trying to recreate that is difficult to tell the exact values. So these are to some extent an educated guess, and that's why you'll see a little bit of difference in these thresholds depending upon the source. A lot of people will ask the question, what's more important in terms of severity of the shock? Is it the current or is it the voltage? And you have to remember Ohm's law, which simply states that if you increase the voltage, you're going to get additional current. So the higher the voltage, the more current you get. So as a result, the higher the voltage, the worse the shock tends to be. One problem is that the electrical resistance of the human body varies from time to time and from person to person. So there is no hard and fast answer in terms of what is a voltage or a current that's safe. It's going to vary. There is some evidence that AC is slightly more dangerous than DC. When I say AC, I mean low frequency, such as power, 60 hertz or 50 hertz. Just a little bit more dangerous than DC, but the difference is very minimal, so it's really best to probably consider them to be equally dangerous. What happens when current flows through your body? Well, in almost all cases, the current is going to override the electrical impulses in your body, and that controls your muscles. And obviously the most serious one would be if it's going to interfere with the muscle contraction of your heart. Then that if it interferes with circulation, then it's a very serious situation. It may also control the skeletal muscles, and you have two possibilities there. It may cause you to freeze. In other words, for your muscles to clamp around the wire and not be able to let go you physically would not be able to overcome that electrical impulse and let go of the source of that current. The other possibility is it may actually act in the opposite direction, cause your muscles to contract in such a way that you're thrown away from the source of shock. But there is also a problem because when you get thrown, you could get physical injuries. And again, I know of a case where somebody was thrown by high voltage and actually broke their neck. So that's also a big consideration. Also, when your current flows through your body, if there's enough current, you get I²R losses, which leads to heating and therefore burning. And that burning can be internal to your body. So your organs may actually suffer a thermal burn. And you wouldn't see that. You wouldn't even know it occurred initially. But obviously it's going to interfere with the function of your organs and can be very, very serious. The pathway that the current takes through your body is very crucial. Here's an example that maybe an electrician might encounter if they grasp an electrical receptacle. They may get a shock as they touch both sides of it, and their current flows from the hot to the neutral through their fingers and through their hand. In that case, the danger is somewhat minimal because the pathway doesn't go through any critical organs. So they'll feel it, but they'll basically more than likely just walk away from a shock like this. On the other hand, if the pathway were different, if the pathway went from that electrician's fingers through their body to their feet, now you'd have a vastly different outcome and something you must be concerned with. But even if it goes through the trunk of the body, then you have to ask, is it going through your core, through your organs, or is it simply passing through the skin? And that's going to vary from time to time. Your resistance of your body will vary over a very wide range. It might be as low as 400 ohms. It might be as high as 600 kiloohms. And that's going to vary from person to person. It also varies from time to time. If you're well hydrated, you tend to have a lower resistance. If your skin is sweaty, you're going to have a lower resistance. And that's when you're going to get greater current. So you have to look at kind of worst case scenario. What's the lowest resistance and what current can we tolerate? And you come up with 50 volts as being something you really need to be concerned with as being potentially lethal. In other words, it doesn't mean if you get a shock at 60 or 75 volts that it's going to be fatal. It just means that given the right circumstances, it may be. So you better be really careful with any voltage greater than 50 volts because, again, under the right conditions, it could be fatal. Generally, under 50 volts, your amount of current you're going to get will be minimal and will be safe and not cause any serious outcomes. The skin resistance is the probably the highest resistance to your body, and there are certain people, particularly medical patients, that have to be very aware of that. If you're getting an IV infusion or if you have a catheter, or certainly if you have external pacemaker leads, these provide a pathway through the skin for electricity, and therefore a much lower voltage can cause a dangerous shock. These people are referred to as being microshock sensitive, and if you're working in the medical field or in a hospital, that's something you should be very aware of. Much lower voltages can have very, very serious consequences for these patients. So what kind of safety precautions should you take? First and most obvious perhaps is to shut off the power on any circuit that you're working on. However, also be aware that a lot of large capacitors can hold sufficient charge to give you a severe electrical shock. Don't work when you're tired or taking medications. And medications, particularly cold medications, are particularly bad for this. Any kind of medication that alleviates cold symptoms tend to be really bad. Remove any watches or rings or any other kind of metallic jewelry. Work only in a dry area. Wear rubber-soled shoes. Keep one hand in your pocket when you're connecting a meter. You may look a little silly, but you don't want to have a second point of contact. Presumably you're already wearing your rubber-soled shoes, so don't make your other hand the second point of contact. And lastly, don't work alone. You need somebody, if you do get an accidental shock, to shut off the electricity, to call for medical help, and so on and so forth. Here's a device that can minimize the effect of electrical shock. It's called a ground fault interrupter. What the ground fault interrupter, or GFI, does is it compares the amount of current leaving a receptacle and the amount coming back on the neutral. Those two currents should be the same. In the event of a fault, there'll be a difference in those currents, and when that happens, the GFI will shut off the current in about 25 milliseconds. The idea there is that fault might in fact be you getting a shock, so we want to shut that off as quickly as possible. It won't necessarily keep you from getting a shock, but by minimizing the length of time that you're exposed to it, hopefully the outcome won't be as serious. Other things you should explore that are related to this are arc flash. That is where you have a short circuit occur on the wiring that is very close to the electrical grid, such as the wire as it first enters into a building. You can have tremendous amounts of energy when that occurs, and that results in a very much localized heating, which would take the metal wires and actually vaporize them, causing explosion, and a very, very serious outcome. And that's an entirely different topic that you should explore. Somewhat related to arc flash is categories of multimeters. If you're measuring voltage near the electric grid, you need a special category of meter. So you should also explore that if you do any kind of electrical work. I hope you learned a little bit about electrical safety here. Obviously, it's just touching the surface of what's out there, but it should provide a good introduction. So thank you for watching, and enjoy not only this video, but also other videos on Mark's Tech Talk. Thanks.